Hello, and welcome to the first video of Computer Science 1300 here at CU Boulder. My name is Michael Hoefer. I'm a second-year PhD student and one of the teaching assistants for the course this fall. So in this first video, I will be discussing the architecture of a computer and how that fits into what we'll be doing for the rest of the course. So the main purpose of this video is to try to explain that computers are fundamentally simple, and they're actually not very smart by themselves. And really the whole idea behind computing and computer science is to take concepts in the mind that we have and make them as simple as possible such that they can be manipulated by a computer. So to start, let's think about a simple device that most of us have used at some point in our lives, a light switch. So I'm here to tell you that computers are really nothing more than a bunch of switches. So it seems crazy, but it's actually true. So our familiar light switch has two states. You can imagine the switch is either up or down, maybe on or off, or as we'll get to, maybe 1 or 0. And we can go up to it and we can interface with that switch. We can interact with it by actually manually going in and flipping the switch. And we can read the value of the state that the switch is in by simply looking at it to see if it's up or down. Now, a single light switch by itself really doesn't do much for us. It can only store one tiny piece of information. In this case, it could be a bit, which is a binary digit. And so we want to add more capability to our computer. We want it to be able to do the things that our computers can do now, display things on the screen, perform calculations. And so what we do is we simply add more switches. So that's the whole secret to computing, is a whole bunch of switches. So instead of our single light switch from before, let's now imagine we have a huge wall of switches right next to each other. And so as programmers, we can go up to this wall and we can pick any switch at random, meaning that we have random access. And we can go in and flip those switches on or off. And so really in a computer, this wall of switches is your random access memory. And if our computers today were simply walls of switches, there'd be so many switches that the wall would actually stretch out for over 1 million miles. And we know that this clearly is not the case. This isn't what happens. We have technology that makes really, really small switches, which we call transistors. And we can put a ton of those transistors, billions of them, into really small components such that they fit in our laptops and smartphones and other things like that. But the idea is all the same, except it's small. So now that things are so tiny and compressed, we run into a few problems. The first one is, how do we actually go in and change the switches now that they're so small? We no longer have a human interface to every single switch. And you can imagine if we were to try to do that by hand, we'd need to be crazy microsurgeons. We'd have to have the best microscope, and we'd have to go in and sort of apply just the right amount of voltage to flip those electronic transistors, those switches. And so that clearly isn't what happens. And so we actually, the role of the microsurgeon is actually the central processing unit, the processor in the computer. And so of course we'd also have to be able to look at those switches and make some sense of what they are saying. That alone is a major difficulty. So how do we know what this massive wall really means? A single switch we can understand. Maybe it corresponds to the state of a light bulb, for example. But really, if you think about all these switches, and if we just assume that if it's on, it's a 1, and if it's off, it's a 0, it's really, like if you've ever seen The Matrix, that scrolling wall of numbers. That's really what's going on inside the computer. So our CPU is actually more switches. It's more circuitry that's wired up. And it has the capability to look at that big wall of switches, make some sense of that wall, perform calculations on the information stored in that wall, and then go back and change that. So our wall of switches is our random access memory. And in most computers, if you lose power, all the switches reset. They all go back to 0. So that's a problem, especially if you want to, like, say, store an image on a computer. And so you can imagine that we could take a picture of that wall of switches and we could save the state of every single switch, and we could put that somewhere else. And that's what your hard disk is doing. It's basically saving the state of a bunch of switches and saving it so that when you turn off your computer, you can load back in your saved state back into your RAM or into your wall of switches. So in the next video, we're going to start to understand how we would make sense of these switches. How do we take all these complex ideas that we have in our heads and that we see on our screens, like Google search engine, or applications on a phone or a watch? How do we sort of take what we want to have happen in our mind and in that human-computer interface, and how do we make that so simple that it can be encoded into a bunch of switches? And most computers use a binary numbering system to do that. So there'll be a short video on binary, and then we'll sort of get into the process of taking what's in our mind and working through levels of abstraction to encode our ideas into a wall of switches such that they can be used by the computer. Thank you.